Welcome back everybody to our course on memory device technology for AIML computing. I am your instructor Dr. Shubhadeep from the electrical engineering at IIT Hyderabad. If you recall, in the previous lecture we concluded our discussion on the fundamentals of SRAM technology, and today we will begin a new topic, the dynamic random access memory technology, or the DRAM memory, and this will be the fourth module in our course. Okay, so let us begin. Just a very quick recap. I hope you can recall this pyramidal structure of memory hierarchy, and as you can see, at the top of the pyramidal hierarchy is your CPU subsystem or your logic subsystem, followed by several memory and storage devices organized in this pyramidal fashion. So in the previous section we finished with the cache memories, the L1, L2 and L3 cache, and the constituent memory element of the cache memory, which is static random access memories, SRAMs. And next we will move on to the main memory part of our discussion, and the constituent memory element of main memory is DRAM, or dynamic random access memory. This DRAM cell constitutes of one transistor and one capacitor only. Okay, so why is this the case? Remember, as we move away from the top, we start compromising on the latency or the speed. The caches are the fastest, the main memory is slower than the caches, and then is your primary storage or your secondary storage. Okay, so while we compromise on latency, what we are trying to optimize or increase, as shown by the base of the triangle in the memory hierarchy, we are trying to optimize for higher and higher bit density or larger and larger memory capacity. Okay, so this we have been discussing for quite some time, and therefore while your L1, L2 and L3 caches constituted of the 6T SRAM cell constituting of 6 transistors. Sometimes we also saw in the last class it can constitute of 8 transistors in scale technology nodes. But the main memory, since it has to give you higher bit density, you have to work with a simpler structure, and this is what the logic of using the 1T 1C structure is. Also recall what is the meaning of the word dynamic random access memory. It means that unlike your static random access memory, SRAM, where the data, once it is stored, cannot be erased until you switch off power supply. So all of these memory elements, as you know, unlike storage, are all volatile. But the speciality of SRAM is that once you store the data, it does not get erased off until you switch off power supply. However, in dynamic random access memory or DRAM, what we will be studying, you have to keep dynamically refreshing the data again and again at periodic intervals of time, because the data which is stored at this storage node of the capacitor, we will see the working mechanism in detail, but I'm just giving you an overview of what is the meaning of this word dynamic. You have to keep refreshing the DRAM cell again and again dynamically, because the data or the charge which is stored on the storage node, which I have marked over here, starts leaking away, because capacitors are inherently leaky in nature. Okay, any realistic capacitor is leaky in nature, and this is what places some serious constraints on what could be the speed of operation of dynamic random access memories. So the point I'm trying to make is, while you make the structure simpler by having a 1T 1C and therefore higher bit density, the price or the penalty you pay is in terms of latency. And this will become clear as we discuss further. Okay. Another important aspect. So again, this is a recall of what we had seen. This is a different way to represent the memory hierarchy. Just recall, the dynamic random access memory comes as the first off-chip element. Remember the CPU subsystem. This is the CPU subsystem chip consisting of your cores, your registers, and your L1, L2, and L3 caches, and your DRAM or your main memory constitutes as the first off-chip memory element. Why is it off-chip? Why can't you include the main memory also in the same die or in the same chip as the logic or the CPU? Remember, the answer for that is that our DRAM cells constitute of the 1T and 1C architecture. Now, this fabrication of 1C or the process technology for the capacitive element is not very trivial. We will go into detail later on. I'm just giving you a heads up. This is very, very different from the fabrication of advanced technology nodes. So, the incompatibility between the two processes makes it more economically and technically viable to fabricate transistors which constitute the advanced technology node in a separate facility and DRAM cells in a completely different facility, and then join them together through off-chip interconnects. Okay, this is the first point. The second important point to recognize is that your main memory, what is the function of the main memory? The objective of main memory is essentially to store data required by the CPU which is of immediate or most frequent needs. Okay, so this data is stored in volatile form, and this constitutes of data and of programs, right? So it has instructions and both the data. And as you can understand, when computing systems become more complex and are supposed to handle more number of cores and more number of operations, the requirements of size of main memory also start increasing quite drastically. And often whenever we buy a computer system or a mobile, we see that the size of the main memory, it could be 8 GB, 16 GB, 32 GB, often is related to the performance of the overall computing system and also increases the cost of the computer or mobile phone that you are trying to buy. So in modern day systems, the latency that you expect from main memory or DRAM systems is roughly in the order of 10 to 100 nanoseconds, hundreds of nanoseconds, and you are expecting that the size that it has to offer is in the order of gigabytes. Now this is completely different from your cache memory, where you were expecting to have only few kilo or megabytes of capacity, but very low latency in the orders of 0.1 nanoseconds to 1 nanosecond. Here you are compromising on latency for higher capacity, right? So a very good analogy that you can give in this to understand what the performance or what is expected from main memory is that of a cricketing analogy. So in our country, cricketing analogies work very well. Students understand it very well. So the best analogy to give is, from DRAM, you are expecting what you expect in a all-rounder in a cricket team. So in a cricket team, you have specialized batsmen and you have specialized bowlers, but often there are these individuals that are required in the team or team players who know a bit of both batting and bowling, right? So these all-rounders often win you the matches, right? And this is what is also expected from the dynamic random access memory, which constitutes the main memory in a computing system, right? So compared to cache, as I just discussed, you would want that the latency can be compromised a bit, but you need to have much higher capacity. But when you compare with your main storage, you would expect that the latencies are much smaller than main storage, but you can compromise on the bit density or the storage capacity. So in essence, DRAM technology has this all-round requirement where you are focusing both on performance and storage density. And engineering these systems is the challenge that we want to discuss in today's class. Okay, so let us move ahead. And before we go into more technical details, let us look at a very brief but interesting historical perspective of how the DRAM technology came about. So the first patent of the 1T 1C DRAM cell. So I have given the layout of the patent from 1968, was filed by IBM by this very famous scientist called Robert Dennard. So where have you heard the name of Robert Dennard? So Robert Dennard was this brilliant scientist at that time working in IBM, and you may have heard the name of Robert Dennard from the Dennard's law of scaling. What is the Dennard's law of scaling? Dennard's law of scaling gives the prescription of how you have to scale the dimensions of the transistor so that you are not compromising on the performance of the transistor. So what Dennard came up with was with the first prescription of scaling, which was the constant electric field scaling. So anybody who has done a basic course on semiconductor devices must have heard his name surely. So his idea was very simple. Like I was showing in the previous slide, you just have a 1T and 1C structure which is arranged in a array fashion, and in this structure the data is stored as a charge in the capacitor in the storage node. Okay, so this was the first idea patent that was filed by Robert Dennard. So however, the first commercialization came very quickly from Intel. So Intel's first chip called 1103 came up with the 3T1C DRAM cell. Now from 1T 1C we are discussing about 3T1C. So here I have shown you the structure of the 3T1C SRAM cell, and immediately you would know that it is two extra transistors. Let me tell you which are the extra transistors. It is Q1 and Q2, two extra transistors over the regular 1T 1C DRAM cell. And if you look at it very carefully and try to relate it to what we were studying in the previous class, you will see some similarity. So the people who have been able to recognize this familiarity, congratulations. So the familiarity comes from the fact that the same concept was used in the 8T SRAM cell also. In the 8T SRAM cell, there were two extra transistors which were added to the 6T SRAM cell to decouple read and write, right? And here you were able to decouple the read from the write because from the storage node you were not resistively reading out the read data, but you are capacitively reading out the read data. So even in this case, the storage node is capacitively coupled to the Q1 transistor, and therefore you can in principle do a non-destructive read, which is not possible in 1T 1C DRAM cells. Okay, and with this technology you were able to go and make the first 1 kilobit. Now it seems very ancient. Now we have gigabytes. But the first DRAM chip, which was an integrated circuit on its own, just had 1 kilobit of data, and it was fabricated from a PMOS design, which had a channel length of 8 microns. Now this was used extensively for the main memory in your old HP 9800 printers, and however, although this was a successful technology, it had a very short shelf life, only from 1970 to 1979. Why was this the case? Why, despite being very successful, was this kind of 3T1C DRAM cell abandoned? The reason is very simple. What we studied in the previous slide is that you have a very severe constraint on the size that a DRAM cell can occupy. You need to have it as small as possible so that memory density can be very high. Adding these 2 extra transistors can be very detrimental in improving the memory bit density, and therefore we realized, or people realized, that you have to go back to the 1T 1C DRAM cell, and that since 1974 has been the staple. Even the DRAM or which we use in main memories in modern day computing only contains of the 1T 1C cell. So very good idea, 3T 1C, but it had a very short shelf life. So the first chip which contained the 1T 1C cell was the MK4096. So the 4096 basically tells you what is the capacity of the DRAM cell. It was 4 kilobits, and it was also used in HP printers, 9800 printers, and it used the first time the NMOS aluminum gate technology. For people who are familiar with transistor technology will know that before polysilicon was used as the gate material, we were first using aluminum gate, and if I am not mistaken, this was the 4 or 1 micrometer channel NMOS aluminum gate. Okay, the interesting part of this design was, for the first time, we have discussed in detail in the first or second week of our course, the importance of memory peripheral circuitry in having very dense memories, right? In accessing very dense memories. And for the first time, the concept of address multiplexing was used. So a 6-bit address was used to access the memory locations. But what was very interesting is that the data was only 1 bit. Basically, you were reading out the data serially, 1 bit at a time. So as you can imagine, the speed of these 1T 1C MK4096 cells were very, very low. Cut to our modern era, where we have been able to improve the performance of the DRAM cell quite drastically. So you may not be able to read, so because the script is a bit small. Since last few decades, we have been able to aggressively scale the technology node of the DRAM cell, and therefore improve exponentially the bit density or the amount of memory GB per millimeter squared. And all of this has been possible because of 2 key reasons. At the device level, you have been able to do aggressive scaling of the transistor, part of which we have discussed even in our SRAM portion. But if you want a more detailed description, I would suggest to look up a course on semiconductor devices. However, in this course, we will talk about a much more important aspect, which is the scaling of the capacitive node or the capacitor. The scaling of the capacitor has revolutionized the performance of the DRAM cell. Not only that, as we will see, even intelligent system level design, which we will focus on, has been very, very important in trying to improve the performance of the DRAM subsystem. Why has all this been important? What has been the key challenge in the interfacing of the CPU subsystem with the main memory? This is what we will discuss, and this will give you the importance of why the subsystem architecture of DRAM cell is also very important and probably one of the most contributing factors of why we have such successful integration of DRAM as the main memory. So the first thing is that very soon people realize that we are hitting a memory wall. What is the meaning of this technical term of memory wall? So the term memory wall simply means that there is a big difference in how quickly your performance of your logic subsystem is improving versus that of the DRAM. So there is a big gap in the improvement of the processor subsystem and the main memory or DRAM subsystem. Why is this the case? This is because while transistor scaling has continued at a very rapid pace, the DRAM scaling or the shrinking of the dimensional aspects of DRAM has been very, very challenging. Okay, to couple the problem or to multiply the problem or to double the problem, I would say, the multi-core parallelism in processor units has made processor units very, very hungry for larger and larger throughput from the main memory subsystem. However, at the same time, speed improvements in the DRAM subsystem has become very, very challenging. It is not as easy to have rapid improvements in the speed of and throughput of DRAM subsystem. The third important point is recognize that DRAM is the first off-chip element, and the moment you have off-chip elements, as we have been discussing, latency becomes a big issue because of the interconnect parasitic and delays. So you have two separate chips. The wires that will connect the two separate chips will have its own delays due to parasitics, and these have been also very difficult to manage. So the best way to understand this is to have to compare the improvements in performance of the processor subsystem versus the DRAM subsystem. As you can see, the processor subsystem has been roughly improving at the rate of 2x every 1.5 years or 18 months. This is basically what is the fundamental of the Moore law of transistor scaling. However, the DRAM memory, if you see, has shown the performance enhancement at a much slower rate. DRAM's performance is only increasing by 2 times every 5 to 8 years. And this has become a big problem. This is because as years pass by, there is a growing difference in the throughput. Between the processor subsystem and the DRAM memory. That simply means that the processor can process data at a much higher rate and is much hungrier for data than the throughput of the DRAM memory subsystem. And this growing gap is called the memory wall or the processor memory performance gap or the memory wall. Okay. If you think this is a big problem for traditional computing systems, modern day AI ML computing has made matters even worse. This is because, as we have been discussing, AI based computing is essentially data driven computing. And in data driven computing, the hungriness of the processor to receive data from the storage and memory elements is much higher. So here, if we see the normalized performance improvements, we see that the flops per second, which is what is flops? It is the floating point operations per second that your processor can crunch out, is improving at a rate of 3.1x every 2 years. However, the DRAM bandwidth is only increasing by only 1.4x every 2 years. To make matters worse, the interconnect bandwidth also is not improving much, only 1.4x every 2 years. So this performance mismatch causes this even more severe memory wall when it comes to AI systems. So this is a problem that needs special attention, and several solutions have been proposed to address this growing memory wall. The first thing that people tried was the traditional approach. So you have a processor subsystem that is demanding data at much higher rate, but individual DRAM banks or individual DRAM cells or arrays are not able to keep up with that amount of throughput. So what do? You do a very smart DRAM subsystem architecture design so that you can encode or you can bring in some parallelism where some banks are active at some time, where information can be supplied through other banks. And this is how somehow you are trying to manage this growing divide between the memory performance and the DRAM bandwidth. Okay. The other approach is at the device level, where you are using embedded DRAMs and new forms of heterogeneous integration and packaging technology to significantly cut down the interconnect delay or the interconnect parasitics which happen between the memory subsystem and the processor subsystem and the main memory DRAM subsystem. The philosophy is very simple. In embedded DRAM, you try to have a DRAM as an on-chip element, and in packaging technology, you use heterogeneous integration such that you can integrate again the DRAM die in the same package as the processor subsystem. But in line with the philosophy of our course, first we will take a top-down approach. So the next class we will see how through advances in the DRAM subsystem you are able to include parallelism and therefore somehow circumvent the memory wall. Then we will look at the details of the DRAM cell and its DRAM operation, and at the last we will look at how through advances in eDRAM and packaging technology you are also attacking the problem from another perspective. Okay, so let us conclude our discussion today, and I will see you in the next session. Thank you.